Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back again to this online NPTEL structural geology course. We are going to start a new week, week 11, and the topic of this week as decided was ductile shear zones, but as I said in the last lecture, we'll spill few of our materials of the faults to this week, and in order to do that, we'll start this lecture, which is lecture number 30. And we'll learn a little bit more on faults and faulting. Particularly, we'll focus on reverse faults. So in this lecture, we mostly cover typical characteristics of reverse faults, as I was talking about. And then we'll look with a particular slide that how to identify faults in the field, because it's not necessarily you see the fault scarp or a fault plane exposed, but there are few other criteria from very small scale to very large scale by which you can identify the faults in the field. We'll very briefly discuss this part as well. So we learnt about reverse faults in the last lecture, and we know that reverse faults, also known as contractional faults, it shortens the crust, and reverse faults are generally those which have dominant deep slip components with a relative upward movement of the hanging wall, and reverse faults which has a relatively low deep angle less than 30 degrees are known as thrust faults. So as you can see in this fantastic image by Foysen, that this is the trace of the fault, this one, and we can see that this particular white layer, this one and this one, they were once upon a time together, but due to the faulting, thrust faulting or reverse faulting, this has moved, and therefore the entire crust got shortened. And this you see in every scale, from very micro scale to regional orogenic belts, and also in subduction zones. As we have understood from our previous lectures, that most of the rocks in the earth are generally under compression, so reverse faults are extremely common, particularly in subduction zones and contractional orogenic belts. So here are a few characteristics of the reverse faults as I was talking about. Reverse faults with a low angle dip less than 30 degrees are generally called thrusts or thrust faults, and the term thrust fault is usually restricted to large scale structures. And in this restricted sense, a thrust fault is generally defined as a map scale contractional fault or a fault which shortens an arbitrary datum line or a lithology in general. Now, thrust faults may show large horizontal displacements in the scale of a few kilometers, of tens of kilometers. If the foot wall stays in the position and the hanging wall is transported, that means the hanging wall is moving over the foot wall, then the thrust is called an overthrust. And if the opposite happens, that means the foot wall moves instead of the hanging wall, so hanging wall stays in a fixed position but the foot wall below is moving, then this is called underthrust. Now the hanging wall rocks which travelled long distance over a very low angle thrust fault is generally called thrust sheet. Now this overthrust, underthrust, these are some tectonic terms that people generally use, so we will not go into that part in detail, but we mostly look at some other features, few of them we have already learned. Now if a tectonic unit has moved, for example, far over the rocks in front of it, that means it doesn't stay in its original position, so it's mostly due to overthrusts. Then we'll have learnt it previously, we have also seen this illustration, then this is known as allochthonous unit. Now a rock mass which has not moved over other rocks described as autochthonous. So for example here this is an autochthon because it stays at its original position in its deposition site, but this blue rock that we see or blue unit that we see here, it has moved far from this side and it is now staying here. Now there are also some erosional features, and there is also another term that we'd like to introduce here that we did not learn before, that is para-autochthonous. So para-autochthonous rocks are those which have moved over the rocks with a small extent. So it did not move a large extent but a small extent, and this large and small, these are generally relative terms with respect to the orogenic setting. Now we also have learned two terms, windows and clippe. These are erosion related exposures. So a closed outcrop of a thrust sheet isolated from the main mass by erosion is called clippe, which you see here. And in contrary, you can say that, I mean, if you have an allochthonous material, which is the blue one, and if that gets eroded like here and it exposes within it the autochthonous rock, then this is known as window, or sometimes people call it also tectonic window. Now in this context, there is also one more term that I would like to introduce here to you. This is called is nappe. So generally it is called nappe or thrust nappe. Thrust nappe is an allochthonous tectonic sheet which has moved over a thrust fault. Now this can happen in two different ways. What I mean by this is that it can involve a thrusting or it may not involve a thrusting. But generally it is associated with folding. So a fold nappe is an allochthonous lithounit which exhibits large scale stratigraphic inversion and may have initiated from a large recumbent fold. So for example, you see here, if you remember, recumbent fold are something like a fold which has its axial plane horizontal. And now if this side it gets a significant movement, then you end up with a structure what we see here, and it does not involve any thrust. So this part was initially probably somewhere here and it moved a long distance, and in that case this is known as fold nappe without thrusting. So the underlying limbs of these folds sometimes may be sheared out into the thrust faults, as you can see here. So this is a sheared unit. So along this the thrust has happened. So if I can consider that while this is happening, this got thinned enough and then it just broke, and then the travel becomes much easier. In that case, this is also known as fold nappe or thrust nappe due to thrusting. Now these kind of structures you see in alpine orogeny, fantastic. So here I show you two examples, rather one example, one photograph taken from panoramic view, but let's look at the first one. So we have seen this is Morkel nappe in one of our first lectures. So you see that the trace of the fold here is going like this, and this got folded and it coming here and like this, and the other layer is something like that. And if we see it here in this panoramic view, the fold is going something like that. So you see it has moved a long distance, and this can only happen if you have a thrust somewhere below. And this sheet here is actually going above, this is thrust sheet. And this is moving due to tectonic movements above the thrust fault. It is in a different position, and therefore this is also allochthonous. Now when we learned this allochthonous, autochthonous, clippe, window, these are mostly related to thrust faults. It is also important to understand right now that how does a thrust fault initiate. Now when the fault is nucleated within a volume of rocks, it initially forms, if I can draw it here, so a very little penny shaped crack. And this crack has a closed boundary, and the top part of this boundary, when it starts propagating, if it propagates in this direction, then this is known as tip line. Or you can say this one in this illustration, that this is tip line. Now one point is very important to remember here, that displacement at the tip line is 0. So therefore this is also a definition of tip line. So here the displacement is maximum, and slowly along this the displacement slowly terminates to 0. So the blocks on either side of this fault line slips past each other like this way relatively, and this slip has to decrease to 0 at the tip line. Now beyond the tip line, the material here, so what is happening here? Now you form a zone here which is known as process zone. And sometimes it also involves a little bit of ductile deformation as well. Now as the thrust propagates, the tip line, this tip line here, let me clean this place. The tip line here also starts migrating. Now as long as the tip line of the thrust fault does not reach the ground surface, so it stays below the surface, then this is known as blind fault. And blind faults are extremely dangerous in terms of producing earthquake, because you don't see sometimes any surface expressions of the fault, and it just stays blindly inside, and if there is any movement, then it just appears on the surface and makes some devastating earthquakes. There are many examples. For example, the Christchurch earthquake in 2011 and 2012. These are examples of earthquakes from the blind faults. People had no clue that there are some faults below the surface. Now many thrusts sometimes, because of this migration upward, sometimes have their upward curving shape, as you can see here. And this can happen only, well, there are many reasons it can happen, but in this case it can happen because this thrust is propagating, so the material here, it is getting pushed upward, and therefore you see this kind of topography. And these are sometimes known as also this kind of faults, also known as listric thrust faults, so that at the base the dip is extremely low or subhorizontal. Let me again clean this space. So here you see the dip is very low, but here the dip slowly increases towards the tip line or at the higher level. Now a thrust sheet emerging on the surface may have traveled on the erosion surface, so for example this one, or on the surface itself, sometimes riding over on its own debris in the front, and this is then called erosion thrust or relief thrust. So sometimes you don't see them on the surface, but this elevation tells you that there could be a fault, and this not necessarily can happen due to thrusting, it can also happen due to folding. Therefore a detailed geological survey is essential to understand whether this surface elevation is just topography due to erosion, or you have some sort of folds down there, or a propagating thrust fault which is blind. Now sometimes this is also the wedge that makes up the frontal portion in the thrust sheet is also known as toe. So this side is known as toe. Now many thrusts as blind thrust and propagate to reach the surface, and they not necessarily, let me clean again here, propagate as a single fault. What I mean by this, that maybe another thrust fault has initiated here, and this thrust fault can also propagate separately, or in the course of their journey they can meet each other, this fault also can split to another fault, and so on. So we always have a master thrust, and then out of this master thrust we have the subsidiary thrusts which can emerge from this master thrust, or some other subsidiary thrusts that can come and join this master thrust, and these all are known as splay faults or simply splay. So while propagating, the thrusts may branch or coalesce with another propagating thrust, and these subsidiary thrusts are known as splay. So here are 4 possibilities I have given here, and these are somehow important. So 2 faults meet along a branch line. So where they meet, I'll show you later in this illustration that what is branch line in this case, and a tip line and a branch line meet at the ground surface at the tip point at a branch point. For ancient faults of the ground surface that we see at present has formed by erosion after the fault movements and has ceased. In contrast, the ground surface at the time of development of the fault is the seen orogenic ground surface. So there is always an interaction between the previous fault and the latest fault. Now, a subsidiary thrust, as I was talking about, may branch out of as splay from the main thrust. Now, this is an example of an isolated splay. So, isolated splay is characterized by the two tip points of the splay are exposed while the trace of the fault is isolated from the main fault stress. So, this is you can consider as master thrust, and this is isolated. So, this has nucleated from here, but it did not touch the master fault. It propagated independently and both of them reached the surface. Okay. So, this is splay fault, and this is an isolated splay fault, to be very specific. Now, sometimes while this is propagating, so this is again the master fault, then you can have a diverging splay. So, this fault is touching the master fault here, and it branches to generate another splay fault, and therefore, this is diverged, or this got diverged from the master fault. So, this is known as diverging splay, as it is written here. Sometimes you may have two faults, so maybe two master faults, one this one, so MF1, and this one MF2, and then you may have a splay fault which is connecting the two faults, and this is known as connecting splay. And then there is rejoining splay fault, which is this one in this case. Again, you have a master fault, and then it diverges from here, say it was like this, and then while it is propagating, it finds it better to meet again the master fault. So, it rejoins the master fault, and therefore, maybe it can look like this. So, these are the branch lines from the master fault to the subsidiary fault inside this fault, and this is known as rejoining splay faults. Now, this is one kind of architecture that the thrusts during its propagation can form, but within this propagating part, as we have learnt about, that these things can move in a different way. So, from the cross section, if we try to look at, sometimes these are known as ramp flat model, and we learn in this slide what is ramp flat model. So, thrust in some regions follow a ramp and flat or a staircase like trajectory. The thrusts cut up section along a ramp and then follows a horizontal zone of flat. As you can see here, that these surfaces are flat. So, these are flat, and then you have some ramp like features which is at an angle to this flat plane, and these are known as ramp, and then it achieves another flat here. So, the ramps can happen in different ways, and we will learn about it, and this is also written here. So, let me explain it in different ways. Now, when the thrust develops in a previously undeformed sedimentary sequence, the flat is parallel to the bedding. So, you see it is originating here, it is parallel to the bedding. So, we saw it, the thrust starts, the dip angle of this fault is very low or almost subhorizontal. Now, if the staircase trajectory develops in a crystalline basement or in a previously folded sedimentary sequence, the flats need not to be bedding parallel, and therefore you generate some sort of ramps, and then it propagates in this way because it just makes its trajectory changed, and then it turns to another ramp. And the ramps, as I was talking about, these are classified according to their orientation with respect to the transport direction. So, this is the transport direction of the thrust, and if the ramps are oriented differently with respect to the transport direction, then we can classify the ramps in a different way. So, as I was talking about, so a frontal ramp, which is this one, strikes roughly perpendicular to the transport direction and has a dominantly reverse slip. So, this is the transport direction, and this is striking almost perpendicular to the propagation direction. So this we call frontal ramp. Then you can have a lateral ramp, which is this one. I'm sorry, this would be ramp. So there should be a lateral ramp that strikes more or less parallel to the propagation direction. So this is the propagation direction, and the orientation, the strike of this lateral ramp is almost parallel to the propagation direction, and this is known as lateral ramp. And the movement along the lateral ramp is interestingly not thrust, but it is mostly strike-slip fault. Then you can have something in between the frontal ramp and lateral ramp, and these are known as oblique ramp. So an oblique ramp strikes obliquely to the transport direction and has both strike and reverse dip slip. So for example here, so this is this propagation direction again, so the strike is at an angle to the propagation direction, and it involves both dip slip and strike slip components along its displacement, and therefore this is mostly an oblique ramp. Now the riding of the thrust sheet over a ramp causes the development of reverse faults, and these are very, very interesting. So flat topped anticline, so you can see that you are actually generating a fold-like feature here, and these are very, very interesting in the sense that while the thrust do propagate, they generate an excellent structure which are sometimes very important for tectonic or kinematic analysis, and at the same time these are also important for hydrocarbon reservoir mechanics and so on. So we will learn more about it later, but the concept of a staircase trajectory and the consequent development of hanging wall anticline with the kink-like geometry were later incorporated in a generalized geometric kinematic model of thrust faulting. So therefore these are very, very important. Now according to this model, the foot wall of the thrust remains essentially undeformed, and if that happens, then you have some hanging walls above the foot wall of the thrust fault that can be thick or extremely thin, and that gave rise to very important terms what we see here in this slide. One is thin-skinned tectonics and another is thick-skinned tectonics. So two styles are commonly invoked to describe the thrust tectonics in the context of ramp flat geometry. As I was talking about, one is thin-skinned and another is thick-skinned tectonics. They mostly refer to the degree of basement involvement in the considered thrust system. So the descriptions are given here, what is thin-skinned and what is thick-skinned. In many fold and thrust belts, the sedimentary cover is detached from the basement. So you have the basement, that is, and then you have metamorphic or igneous complex, and then you have sedimentary layers. Now if the thrust initiates in between the basement and the sedimentary layers, then typically along the fault planes, then it shows the ramp flat geometries. Now the sole thrusts, we'll learn about it soon. Thrust that is generating at the bottom is known as sole thrust. They remain above the strong crystalline basement, and the crystalline basement remain virtually undeformed. Now this style of deformation is known as thin-skinned tectonics. Then bedding plays a controlling factor, so the composition, the rheology and so on, these are very important parameters in generating the staircase or ramp flat systems. In contrary, the thick-skinned tectonics in metamorphic regions, thrusting is commonly associated with intense and distributed ductile deformations, where the deformation is happening at relatively high pressure and temperature. In that case, the staircase, flat and ramp geometry is generally not expected. So major sole thrust extends steeply down the basement, so it involves the basement, either metamorphic or igneous, although the thrust zones tend to follow staircase of rheological contrast, they involve the basement. The style is termed as thick-skinned tectonics. So in these following slides, we will not separate what is thick-skinned and thin-skinned in illustrating the diagrams and the processes, but you can think of that mostly sedimentary layers are being involved in these processes. So in a way you can think that these are mostly thin-skinned. Now let's talk about how do these thrusts propagate. They do work in a single fault or there are multiple faults. We learned that it involves multiple faults which are known as splays, but we'd look at these things now in a different way, which is relevant for the large scale tectonics. And we start with the term called thrust imbrications. Now thrusts in mountain chains generally occur in groups, so you don't have a single thrust. Now you can just quickly think of the thrusts in Himalaya, the major thrusts, this MBT, MCT, STD and so on. So they are in a group, not necessarily they occur at the same time, and this is exactly what we are going to learn in this slide. So the geometrical interrelations among the members of such thrust systems have been intensively studied, and this is a topic of research in most of the cases, and people do experiments, numerical modeling and also intense field survey to understand the thrust mechanisms and how do this group of thrusts do evolve. A prominent low angle thrust occurs beneath some thrust systems. This is called floor thrust or sole thrust. Let's explain this one after another. So this is your initial setting, tectonic setting, where everything is in peace, nothing has happened. And then there was a push from this side and this material started moving in this side. Now when that happens, due to contraction, it may generate a thrust in this way. This red line is the active thrust here. Now if this deformation continues, then interestingly it generates another thrust in the front of the previous thrust. So this is my first thrust and this is the second thrust. The second thrust, interestingly, this thrust line here is become passive. So there is no displacement along this line. So this becomes passive or inactive. But it does rotate backwards, and while it rotates, it slightly achieves a topographic high, while the second thrust is moving with an active thrusting along its boundary. If the deformation continues further, it generates another thrust, which is thrust number 3. So this was the 2, this was the 1. Then it takes the deformation, most of the deformation. This was already inactive and this becomes also inactive. Now everything is happening and they are merging on a horizontal or subhorizontal surface which is also slipping, and this is known as sole or floor thrust. And these subsidiary thrusts which are emerging from the sole or floor thrusts are known as imbricate thrusts. Interestingly, these previous thrusts, previous imbricated thrusts 1 and 2 in this case, they again rotate back. So this rotates, the first one rotates further towards this side, and sometimes to accommodate the rotation it produces a fault. This is also a thrust fault which is verging oppositely, and this is known as back thrust. I think I gave the sense oppositely. The drawing should be something like that. So you don't worry about this part. Yeah, the drawing is a little bit wrong. It should be something like that as I try to correct it. So, and while doing this back rotation and also the combination with the back thrusts, the topographic elevation is achieved. So you see that this is here and this much height we have achieved to this process. Now this process is known as thrust imbrications. The series of thrusts that we see here, these are known as imbricated thrusts. So to describe this process in a different way, let me explain in detail. So the sole thrust is the lowest regional thrust surface. In some cases, subsidiary faults may splay upward from the floor thrust and may cause a tile-like piling of the subsidiary thrust sheets. This is exactly what we have seen here. This arrangement of the subsidiary thrust is known as imbricate structure. As we have named it, it's also known as Schuppen structure. Now this imbricate faults, they meet on the floor thrust asymptotically, as you can see here, they meet the floor thrust and curve upward with increasing dips at higher levels. And this is the characteristics of thrust faults we have learned. So in a trailing imbricate fan, the thrusts, so they actually produce something which is called fan also, thrust fanning. So they just move this way like a fan. And these thrust fannings, or sometimes their rear shows the maximum sleep. An imbricate zone or an imbricate stack may be confined between a floor and roof thrust. We'll learn about it. So what I mean by that, that here the top part is, at least in this drawing, is somehow empty. But you can have another thrust at the top, and then it is known as roof thrust, and it is known as duplex structure. We'll learn about it soon. So for an example, you can think about the faults in Himalaya, that we have series of thrust faults starting from the north. We have STD, MCT, MBT, and in this case JMT and MFT. Now from your stratigraphy or tectonics lecture, you may have learned that MFT is the youngest fault, then and STD is the oldest one. So this is where things started. And then initially, first we formed this, then this, then this, and now this one. So this is exactly what we have seen in the previous illustration, that one after another this imbrication thrust is propagating, and in this case the floor or sole thrust is MHT, the main Himalayan thrust. People generally study these kind of things with sandbox models. And here I have given an example from one of my juniors, Pushpendu. He performed these experiments and that got published in a paper. So here you can see that, first of all, these are the imbrications. The floor thrust is somewhere here, which is moving this way. And in his experiment, he has generated a series of thrust faults. And you can also see the back thrusts here. These have formed. And interestingly, you see while doing this, the topographic elevations are achieved. The angle of this frontest imbrication is less compared to the imbrication at the backside, the first imbrication that we have formed in this experiment. So by experiments, people also study a lot, and these are functions that what will be the spacing of these faults, how much they will rotate, and so on, is essentially, there are many parameters that control this. So one is this friction along this sole thrust, then the materials you are involving, the height you are achieving, and so on. So all these things do play a very interesting role, and people are still studying this, that what causes these imbrications and the elevation of the mountains, because this is one of the most important mountain building process. Now we'll go to what I was talking about, this duplex structure. So when imbrications do happen, and it has a sole or floor thrust, and it also has a roof thrust at the top. So if a roof thrust bounds the imbricated zone upward, then the complete structure is called a duplex structure, and it generally develops in sequence. So a duplex consists of horses that are arranged piggyback. So let's try to understand this. So we have this sequence, maybe one before, and then we have developed this ramp flat model. This is the flat. Then we have the ramp. And then we have again a flat. Now this is the sole thrust or the floor thrust. And then if we have a significant amount of sedimentary cover at the top, it may not involve the entire sequence. So we can have also a thrust at the roof in the next segment, and this is known as roof thrust. And these individual segments, while doing it, it would also produce imbricate thrusts, and these individual segment, this one, or in this case may not be, but in the next sequence we will see that these are known as horses, or a single imbrication. that we see is horse. So this is a horse, you can see confined here. This is another horse. So it continues this way. We'll see an animation in the next slide how to this form. So you have your sole thrusts, which is marked by this thick black line. Then you have imbricate thrusts, and you also have roof thrust going here. So if an imbrication zone is restricted between sole or floor thrust and roof thrust, then this is known as duplex structure. So the horses typically have an S or Z shaped geometry. So here it is like Z, but if you see it in the other way around, if the movement was from this direction, then it would form something like that. And then, so this is your roof thrust, this is your floor thrust, and then this would produce something horses like SS, S-shaped structure. And then they tend to dip towards the hinterland. So in this case, this is your hinterland. And the horses can be also folded, faulted, and rotated during the thrusting history, and they produce some fantastic structures. We'll learn about it soon, so that their primary geometries and the orientations become modified. So you may see that this is the hinterland side. In this hinterland side, you may see that the imbrication closest towards the hinterland may have a higher angle compared to the angle which is farthest from the hinterland. But let's see an animation how do this form. So this is an animation I collected from the internet. So you see this is how this duplex structure do form. This is your sole thrust. These are your imbrications, this red lines here, and you have your roof thrust there. Now, do we see in the field of this kind of structures? Yes, we see them in many different scales. So here is an excellent example from the same page from where I took this animation. So looking at it, you can clearly now identify from this illustration that we have seen that this is certainly a thrust plane, and this is your floor thrust. And there is also one more here going like this, and this is your roof thrust. And between the floor and roof thrust, you have the imbrications like this. Don't mix it with cross bedding. This is tectonic process. Okay, so you see this complex structure here. So this individual blocks here, this one, it has moved this way. So this is the orientation of the thrust here, and these are known as your, that we have just learned, horse. So individual horses, and each of them slipped this way. This is an excellent example of this duplex structure. So you have roof thrust, you have floor thrust, in between you have series of imbrications defining the horses, and so on. We have one more example from the book of Professor Foyson. So here again you have roof thrust, you have this one, you have floor thrusts here, and in between you already have marked, you have the horse, individual horse, and you see they are dipping this side, all these horses, so this must be your hinterland side. And this entire structure is known as duplex structure. So you have now very clear idea what is imbrication, what is sole thrust, or floor thrust, what is roof thrust, what is duplex, what is piggyback, and so on. Now this kind of structure, so in these imbrications do happen during thrusting, they produce two very interesting kinds of folds. One is known as fault bend fold and another is known as fault propagation fold. When I was a student, I was extremely confused that which one is what. Later it got clear to me, but I believe with this lecture you will never confuse what is fault bend fold and what is fault propagation fold. Two very commonly used terms in structural geology. Sometimes people also ask in the interviews and so on. Now, fault bend fold is essentially a structure that you see in the ramp flat model. So the moment a ramp is established and the hanging wall starts climbing above it, the hanging wall layers are deformed into a fault bend fold, as you can see here. This is the flat, this is the ramp, and this is again another flat. And the movement along this ramp flat is this way. Now this hanging wall materials, sedimentary layers, it has to ride over this ramp flat. So when it does it, because we have a ramp here, it has to produce a fold-like structure. So the layers over the ramp, when it rides, it has to bend to accommodate the space. And therefore, this is known as fault bend fold. When the layers, the hanging wall layers got bended along a fault plane is fault bend fold. This term along is very important. The geometry of the fold reflects the geometry of the ramp. Angular ramps produce angular folds, kink-like folds, while more gently curved ramps, which you see here, this is not as sharp as the illustration we have above. So also the folds we form, these are very gentle and curvy folds. So you can have this, you can have this, and these are known as fault bend fold. Now this is how do they occur in sequence. So this is your first stage. So T1, then T2, then T3, then T4, and then T5. So this is the initiation of this ramp flat model. So again, this is the flat, this is the ramp, and this is again a flat. Now when that happens, when this hanging wall materials are trying to ride over this ramp flat, then it has to produce a kink-like feature at the forelimb, and this is known as growth of the forelimb. And then it also has to adjust at the back side, so this is known as back limb. And then with time it propagates, the forelimb expands, back limb also develops, it achieves a topographic elevation, and so on, and finally it appears a fold-like feature. And this is the process we form the fault bend fold. Now interestingly, you see in this entire illustration, the footwall rocks, they are virtually undeformed. So everything is moving on the top side. The hanging wall is taking all the deformation. Now this is an example of a fault bend fold. You see here that this is the thrust propagating like this. So this one is your footwall, and this part is the hanging wall. And you see, due to riding, it is producing a structure. It has to produce, you also have some back thrusts here, and it is going like this. And this is fault bend fold, a classic example of fault bend fold. And you can have another thing which is fault propagation fold. Now many reverse and thrust faults form a ductile fold zone around their tips, and they form to propagate. This is very important. fault bend fold is along the fault. The geometry of the fault bend fold is defined by the ramp flat of this thrust involved in this process. But fault propagation fold is essentially controlled and also nucleated from the tip of a propagating fault. So these are the basic difference between fault propagation fold and fault bend fold. We will see how do these things occur with this illustration. But the tip fold zone is particularly well developed, where thrust faults affect non and low metamorphic sedimentary rocks. The fold associated with the fault tip is fault propagation fold. Again, the tip is very important, and for fault bend fold it is along. So let's see how does it work in contrast to what we have learned with the fault bend fold. So we have a series of sedimentary layers, and say we have initiated, due to some compression here, a thrust, and this is the tip of the fault. Okay. So it is moving straight, this part is getting contracted, fine. Now because it is a thrust fault, it has a tendency to move upward with a higher dip. Now when it starts moving upward, it first thing it does that at the back side it develops a back limb, at the front side it also develops a forelimb. And with time, when it propagates, it also grows or accentuates the growth of the back limb and the forelimb, and this is how it works. And finally one stays with a structure, a fold-like structure like this. Now geometrically it may appear very, very similar to what we have seen with the fault bend fold, but a fault propagation fold, it may have a very similar geometrical disposition, but the mechanism of development is essentially different. Sometimes you also develop, so in this case if you have a fault where you have movement both on hanging and footwall, so here we see things are happening only on the hanging wall, but the footwall is virtually undeformed. You can also have a thrust like this, where you can have something like that in this side and then something like this in the other side. So both you can have fault propagation fold on the hanging wall side and also on the footwall side. So these are also kind of fault propagation fold that has grown due to the movement of the fault tip line. Let's see some examples. So this is one which I have taken from the book of Professor Foyson. So you see this is the fault plane going, and you have an excellent fault propagation fold here in this structure. You can also see here that that example I gave you, you have this is the thrust plane, so it is moving this way. And then what we see here, that we have fault propagation fold in this side, and we also do have fault propagation fold in this side. So this is how you define the fault propagation fold in 2-3 different ways. But I am sure with this presentation or with these illustrations, it is now very clear to you the difference between fault bend fold and fault propagation fold. Now what we are going to do, that last topic of this lecture, that how do you identify faults in the field. Now there are several criteria in recognizing the faults, particularly in the field or also from a map. So even when the fault line is mapped, the dip of the fault plane may not be measurable. The dip can be measured in certain circumstances. For example, you can think of when a fault trace is exposed in areas of high reliefs, that means the fault surface itself is exposed and so on. I mean, if someone does some drilling work and other things, so by this you can measure. But the challenge is to identify the faults in the field. So there are several criteria which I have listed here. The first one is the geological mapping. So faults are sometimes recognized by abrupt terminations of beds against a line on the map. You can also think that abrupt termination of beds along a line of a sharply defined structural discontinuity, if that you see in your map. You also can figure out as a fault in the field, but you have to be very sure that this is not some sort of angular discontinuity. So you have to separate or rule out the possibility of angular discontinuity with respect to the sharply defined structural discontinuity. Now, you can also identify the faults if you have seen repetition or omission of beds. Now, we did not learn what is repetition or omission of beds, but we learned it with respect to the fold. So, in fault you can have repetitive layers or some layers are missing. Now, it is also important that repetition of beds you also can find, or it can result also due to folding. However, in the case of repetition in fold, it is symmetrical. So, repetition of beds caused by fault is essentially asymmetric, and that can help you to figure out that you are somewhere near the fault zones. Now, faults can often be located by the occurrence of fault breccias. So, if you see highly crushed rocks, we have seen before in the deformation mechanism lectures, along a continuous or discontinuous line. So, that tells you there must be some sort of faults around you. Some fault planes also contain a pulverized clay-like materials, or which we call fault gouge, and you can also figure out that if you see some slickened sides like features or polished striated surfaces subparallel to the fault plane, that also tells you that you are in a fault zone. Now, in certain places a fault plane is directly exposed as a fault scarp, a cliff with a more or less planar slope, that can also tell you that you are in a fault zone. And finally, if you think about the thrust faults, which are large orogenic scales, then because the thrust faults, they travel a long distance, that may bring together rocks of quite dissimilar sedimentary or metamorphic facies, or the rocks of very different ages, they can stay together. That can also happen due to folding, but in thrusts it is more common. And finally, for the subsurface, if you do some seismic imaging, seismic reflection survey and so on, you can also figure out the faults from those images if you know how to interpret that. So these are the different ways that you identify faults in the field. And with this I conclude the lectures on fault. In the next lecture, we'll start the actual topic of this week, which is a ductile shear zone, and we'll first learn its characteristics, and then we'll classify, and there are a series of new things and new terminologies to learn and understand. So stay tuned. I'll meet you in the next lecture. Thank you very much.